We're talking about line integrals. We're talking about work done by forces. And we have the simple situation that I want to do multiple different ways. So the situation is with a surprise and a question. So the situation is basically a block sliding down a frictionless plane, a straight plane. So let's calculate the work done by gravity, the work done by the normal force, two different ways, and then a bonus way. And the work done by the normal force is kind of difficult, but let's just do that. Let's do this the easiest way first. But here we have, it's starting at point x1, y1, goes down to point x2, y2. There's a gravitational force. And we have to have that normal force because if you don't have that normal force, it wouldn't move along that path. So I put it there just to be thorough. Okay, let's do this the simple way. Let's look at the gravitational force. The gravitational force F is going to be 0 x hat minus mg y hat. We define the work along that path as going to be the integral from point 1 to point 2 of f dot dr. Now, let's do this the simple way, because if we have a constant force, I want to calculate the work done by gravity, which is a constant force, and the path is straight, then this dot product is a constant thing, right? So I actually can factor out this constant f dot, which seems silly, but it works. So this is f dot the integral from 1 to 2 dr. But the integral from 1 to 2 of dr is just delta r. So this is equal to f dot delta r, where delta r is the vector from here to there. So let's go ahead and write delta r is going to be the change in x, x2 minus x1, x hat, plus y2 minus y1, y hat. And now I have the force, I have delta r, so the work is going to be, I'm going to write it all explicitly because I care. It's going to be 0, the x component, times this x component. So 0 x2 minus x1 minus mg times y2 minus y1. X components plus the y components. And so this is just equal to negative mg y2 minus y1, or I'm going to put it over here so we can use it later. Work is going to be mg y1 minus y2, right? I had to switch the order there. But that, because y1 is greater than y2, so that says that the work is positive. That means my change in kinetic energy is positive. That means the object speeds up, okay? Which is what we knew. If it's going down that hill, it should be increasing in speed. The work should be positive. Okay, now, what about the work done by the normal force? Okay, now we're going to do this a couple ways, but let's start off with a simple way. So the work done by the normal force, again, I can say N dot delta R. So the simple answer is that the normal force is a force of constraint, and it's perpendicular to the surface. So if I write this as N delta R cosine theta, that's the same thing as the dot product. Well, by definition, the angle's 90 degrees. Cosine 90 is 0. So the work done by the normal force is 0. Okay, and this is where we're going to get into some question in just a second. Is the work done by the normal force always equal to 0? The answer is no, it usually is. Okay, but I'm going to show you two situations. Here's one, and we'll do this later. Here's a block on a movable wedge. So as the block slides down, the wedge can move this way. So the wedge exerts a normal force on the block like that, but the path isn't this way, right? Because the block's going to go down this way because the wedge is moving that way. So they're not perpendicular. So it would do work. It's kind of cool. Now the other case that you're going to see work done by, you could do work done by gravity, is a person in an elevator. It doesn't even have to accelerate. But if you have the normal force, the weight, so now the normal force on the person is in the direction of motion, even though it is a normal force, and it would do work in that system. Okay. Most of the times, not going to do work. Okay, let's use our other definition of the work, a line integral, and do it explicitly and see that we get the same thing for both the gravitational force and the normal force. So now we're going to say work is the integral from 1 to 2 of f dot dr, and I'm going to say dr is the vector dx x hat plus dy y hat. And now I'm going to give you my mandatory reminder that that's always dr. Don't worry about the direction. The direction comes from the limits of integration, not from dr. Again, you know I made that mistake a whole bunch of times. Okay. So let's do this for the gravitational force. The work done by the gravitational force is going to be equal to the integral. I'll just put it from point 1 to point 2 generically. And then I have 0 dot times dx. I'll write it out. And this is all in there. Minus mg times dy. I can write this as two integrals. I can write this as the integral from x1 to x2, 0 dx. And yes, I did that. Minus the integral from y1 to y2, mg dy. Now, we can integrate these. We don't have to do anything special because there's nothing but x's in this integral. I know, and there's 0. And there's nothing but y's here, so they're easy integrals. So if we integrate this, the integral of 0 dx is 0, evaluated at x1 and x2. And the integral right here is going to be minus mgy, evaluated from y1 to y2. So that's going to be negative mg y2 minus y1. Same thing. Same thing. Okay. Now, can we do this with the normal force? Yes. But we do have to do some tricks, right? So we're going to have the same work. We're going to have the same definition. But we need to come up with a vector for the normal force. Look at that. Someone needs to clean their erasers. And that someone's me. OK. So let's say n is equal to nx x hat plus ny y hat. So it has an x and a y component. But I need to know that direction. And I can't take the dot product if I don't know that direction. And any old direction won't work. I have to have the direction. So if I say something weird, if I say n dot delta r has to be 0, I can find that. So let's just say n dot delta r, because they have to be perpendicular. It's going to be nx times x2 minus x1 plus ny times y2 minus y1, and that's going to be equal to 0. I'm going to set that equal to 0. I can pick, if I don't really care about the magnitude of the normal force, I just care about the direction. So we got to think, what could I have for nx and ny such that when I multiply this out, I get 0. And if I just guess and pick it, that's fine. It's going to work. And I'm going to show you what I'm going to pick. Because here you see I have something times x2 minus xy. I have to add it to something times y2 minus y1. So I could pick this. I could say, I'm going to erase it right here, and I'm going to put it in. I'm going to put in my thing. I'm going to say negative a, some constant, times y2 minus y1 x hat plus a times x2 minus x1 y hat. So now when I do the dot product between this and this, right, I'm going to get negative a, x2 minus x1, y2 minus y1, and this one's going to be a, x2 minus x1, y2 minus y1. So they're going to add up and they're going to be 0. So that will work. I don't even care what a is. I know it's cheating. You don't have to tell me. I know. OK. But when you get in a problem that you can't quite grasp, sometimes you just need to cheat. OK. So now let's set up our integral. The work is the integral from, I'm going to go ahead and break it into two integrals, from x1 to x2 of nx dot dx, so it's going to be negative a y2 minus y1 dx, plus the integral from y1 to y2 of a x2 minus x1 dy. I can actually integrate this because these are all constants, right? So this is just, I just multiply it by a constant. So I get work. I can integrate this. I get negative a y2 minus y1, and then x from x1 to x2, so that's going to be x2 minus x1. And over here, I get plus a x2 minus x1, and then I integrate this, I get y from y1 to y2, so I get y2 minus y1. This, same as that. This plus that's 0. Well, that's got a negative. So the work done by this normal force is indeed 0. Did it. Okay. Now you know I like to do Python stuff, so if you want to pause here and you're like, I'm anti-Python, Python bad, don't want to do it, you don't have to do it. Okay. You may be excused. I'm not even gonna pass judgment. Okay, but I want to do this because I want to do this another way. And I don't want to do a numerical line integral where I know the normal force, because the normal force is weird in that we don't really know it, right? It's a force of constraint. On a straight line, it stays the same, but what if the line wasn't straight? How do we deal with that situation? So here's one way that we can model this. Suppose I have a ball. If it's up here, it's not in contact with the surface. The normal force is 0, right? N is 0. But once it's down here, there has to be some force pushing it back up and keeping it below the surface. So there is a force there. And what we can do is to calculate this distance, s, that it goes below the surface. And then I can say it's like a spring. The magnitude of the normal force is some spring constant times s. So I just need to calculate that s, and then I can multiply it like that. And in fact, what I'm actually going to do is to say negative vector in hat. So I'll have my mass. It'll have a gravitational force acting on it. So I can calculate the net force. And the normal force will either be 0 or some value. So F net is going to be N plus mg. And that's going to be the change in momentum with respect to time. I'm going to use momentum principle just because I like it. And so if I break this into short time intervals, I calculate this and I can say it's constant. And then I can use that to update the momentum. I can update the position. And then I can do it for the next time interval and check and see where the mass is. Is it below the thing or not? Now, I do have a problem finding this s. Okay. So the first thing is I'm going to actually cheat with the unit vector in hat. I'm going to say what it is. Okay. So let's say that this is x1, y1, x2, y2. And then for n, what did I do before? Yeah, so I'm going to calculate this vector. I'll call it delta r. I did that before. So this is going to be delta r, that vector right there. And again, just like I did in the previous example, I can say n is going to be equal to the x component of this, the negative y component of this, negative delta r y x hat, plus delta r x y hat. Now, that won't be normalized, so actually, whatever that is, I don't really care. I'm going to then say in hat is the vector n divided by the magnitude of the vector n, and then I'll have that in hat vector. Now, that's important because that can be used to find s. And it's tricks. It's all tricks. Okay, there's tricks all over the place. So what I'm going to do to find s, let's do an extreme case. So here's my ball. I'm going to find this vector r, which is from the start to my ball. And in hat is this way. So you see there that if I take the dot product of this, it'll give me the projection in that direction. So s is just going to be r dot in hat. And that will actually give me this, which seems crazy, but it does. Yeah. And then if it's below here, I'm going to exert a force. If it's above there, I'm not. Okay, let's just get to it and make a mess with Python, because otherwise we're never going to finish. So let's go over to Python. And I already put in my points because I had those same points before. So I have point 1 where it starts, point 2 where it ends, and there's my ball. Let's just run this just so you can see what it looks like. There's my ball, the 2 points right there, and that's fine. Let's go ahead and make a plane, let's call it a plane, even though it's not. It's going to be a cylinder and its position is going to be p1.pos. Axis is going to be p2.pos minus p1.pos. p1.pos. And then the radius, let's put it at 0.01. Let's just try that. Okay, looks good. Okay, now what I want to do is to find, I want to get my in-hat vector. I need some other things. Okay, so let's say I want to put, let's ball.m equals 0, no 1. Ball.p, the momentum is vector 0, 0, 0. It's going to start from rest. I need g, it's going to be vector 0, negative 9.8, 0. I need k, let's go with 1,000. K is going to be my spring constant, right? I want that to be very high, very high. T equals 0. And then my dt time step, I want it to be small too, 0.001, because I want to be able to really adjust that thing so it's not bouncing all over the place like a crazy ball. Okay, in-hat, let's do delta r. So I'll call it dr is p2.pos minus p1.pos. And then in-hat, I'll call it in-hat, is going to be equal to, what did I say that? It's going to be norm vector d negative dr dot y dr dot x 0. So dr is a vector. Dr dot y is the y component of that vector, and then dr dot x is the x component. When I do that all together, I get a vector. And then norm takes the magnitude, divides it by the magnitude of the vector, makes it normalized. So it has a unit vector of 1. So I'm all done. I have in-hat. Okay, let's see. So what else do I need? Let's see. I just want to move it first. So let's just try to move it. Okay. So let's make a loop. I'm going to say while ball.pos.y is greater than p2.pos.y. So I want to say until it gets down to that y value. That can be problematic depending on how you do it, but I think it should work in this case. And then I'm going to put rate. Let's put rate 500. It should be rate of 1,000, right? But I'm going to have it run in half motion, half speed, just so we can see what's going on. The first thing I'm going to do is to set the normal force equal to 0. Because at the beginning of each loop, I'm going to assume that there's no normal force. It might not be in contact with the plane, and then I can change it later if I have to. Now I'm going to calculate that vector r from the first point to my ball. So r is going to be ball.pos minus p1.pos. And now I can calculate s. S equals the dot product of r and in-hat. And I'm pretty sure that works. I'm trying to think, yeah, so I'm looking at my picture, if the ball's below the plane, then the angle between them is going to be greater than 0, and I do get a negative number, so that is important. Okay, so now if that s value is less than 0, I'm going to calculate the normal force. If s less than 0, then there should be a normal force. And that normal force is going to be negative k times s times in-hat. So s is negative, and so this is going to end up being in the direction of in-hat, which is what I want. Okay, otherwise it just doesn't do anything. Now I can calculate the net force. It's going to be n plus m times g. So g has a negative y component, but we don't do minus mg. Now I can update the momentum. Ball.p equals ball.p plus f net times net times dt. Let's see. And now I'm going to update the position. Ball.pos plus ball.p times dt divided by ball.m. So ball.p divided by ball.m is the velocity. So that's velocity times dt. Now I need to update time. T equals t plus dt. And it should work. But it may not. I should probably save it. I should probably save it. Nothing happened. Can't find M. Where did I put in? Aha, right there. Ball.m. Look at that. And look, you can see, if you look closely, you can see where it's kind of like zigzagging along, which is fine, right? It's going below there, the force is pushing it. Let's just increase the spring constant and see if we can get it to work a little bit better. I'm gonna put this at 5,000. I don't even know, I'm just picking something. I mean, you can still see a little bit wiggle, but I'm pretty happy. I'm pretty happy with that. So the ball's moving down there. Now we can calculate, we have the normal force, and so we can calculate the work done by that. Let's just display the normal force just for fun. So over here, I'm going to say in scale equals 0.5. I don't know, because I don't want to display the full normal force. And then in arrow is going to be an arrow. Position is going to be ball.pos. Axis is going to be, ooh, I didn't calculate that. Let's just say n equals vector 0, 0, 0. N is going to be in scale times n, and let's make it color equals color.cyan. Okay, so now in the loop down here, I need to move the arrow and change the axis. So when I move the ball and stuff, I'm going to go down here and say in arrow.pos equals ball.pos, in arrow.axis equals in scale times n. Let's just see what happens. Okay, that's fine. It's getting huge, right? That's actually what we'd expect. Let's make that n scale a lot smaller. Maybe this isn't a great idea to even display that, but let's make this 0.05. Yeah, okay, that's kind of cool. Okay, now I want to calculate the work during each step. So I have the force, I have n, I need delta r. So delta r is just going to be the velocity times dt, right? Because each time step I'm assuming things are constant. So I can do that. Over here, let's calculate the work by first setting the work equal to 0. And then down here, I'm going to calculate the work. So once I have that, I'm going to say d work is going to be n dot n and ball.p times dt divided by ball.m. So ball.p divided by m is the velocity, times dt is that vector displacement. That's dr, right? And then I just dot it with n. And then I'm just going to say work equals work plus d work. And then down here, we're going to print that. And we said it should be 0. And it's not 0. But it's pretty small, right? So what's happening is that, my steps are not always in the same direction as the path because it's springing up and down. So sometimes it's moving in the direction of the normal force and sometimes moving against the direction of the normal force. So you do get some work. That's fine, right? It's just a numerical calculation. Let's go ahead and calculate the work done by gravity. Let's see what happens there. But we do have something very important here because we have a way to model the motion of a ball on a path. We're going to be doing a lot of this stuff later, so I think that in that aspect is important. So let's call this work G. Work G equals 0. And then down here, d work G is going to be the dot product of ball.m times G times the path, ball.p times dt divided by ball.m, right? And then I need to add that to the total. Work G equals work G plus d work G, and then we'll print that out down here. Print work G equals, comma, work G. So you get close to 9.8, so I had a mass of 1, G is 9.8, and delta Y was 1. So that's pretty good. Okay. Whew. You know, sometimes you get scared that things like that won't work, but that worked. And we're going to use this technique, the spring technique, again later, like I said, just to check things. But it's a fun way to play with stuff, and it is pretty fun. I'll put the link to this code down below, and that's that. I'll talk to you later.